this problem, we have to figure out Q in. And remember, Q in is the amount of charge enclosed by the Gaussian surface. So the only thing we have inside our Gaussian surface that has a charge is a portion of this slab. So if we want to find the net amount of charge inside the Gaussian surface, we have to find the net amount of charge on this Gaussian surface that's inside the slab. So why don't we try and shade that in a little bit. Again with the 3D here, not super, but we'll do our best. So we're trying to find that much charge because that's the amount of the charged object inside the Gaussian surface. So that's the charge that we're trying to find. In my 2D picture, it's a little bit easier to visualize. Okay, so this amount of charge equals Q in. And that's what we're trying to find. How do we find this charge? If this were an object with a uniform charge density, it would be easy. We would do the density times the volume of this block. But it's not a uniform charge distribution. So we have to think about how do we add up, how do we find the total charge within this block? So maybe what we can do is let's take this whole block and let's break it into some pretty thin slices. So I'm going to do the 2D drawing first. So if we had a slice here, add this bit, add this bit, add this bit, this bit, this bit, and so on. If we add up all the bits from the bottom to the top, we would get the total charge on this block. So we could add up that bit, and that bit, and that bit, and so on. So let's break the Gaussian surface into slices. Each of those thin slices, and I'll just shade in one of them, each of those thin slices, what do we know about it? It has an amount of charge that we'll call dq. It's only a small amount of charge, which is why we'll use d. So it has charge dq. It has area A. Maybe if I try and draw my slice over here on the 3D picture, it might be easier to see why it has area A. So my slice is a little bit of the charge that goes through the whole thing. Okay, so it has area A, the same area of that Gaussian surface. It has area A. Let's get a coordinate system on there. The vertical position of it is from the center to some height. We're using Z for the Z-axis. And we're going to say that the height up here, we're going to call this guy here Z. So I don't want to use Z for the vertical height right here. I'll use Z primed. Height or vertical position Z primed. The thickness of each slice is from here to here. The thickness is a little bit in the vertical direction. Since it's a little bit in the vertical direction, we'll say it's d times z primed for the thickness. So that's that amount right there, dz primed. Okay, so the total charge on that slice is dq. It has an area A, it has a height or a vertical position of z primed, and a thickness of dz primed. What can we do with this? What can we figure out? If we add up all of the blocks that I've drawn here, I'll get the net charge on the top part of that slab. So Q on the top part of that slab is equal to the sum of every little bit of charge dq. So when we add up each little bit of charge, eventually we'll end up with a total charge. If we're taking these charges to be pretty thin, then a sum of a bunch of small things goes to an integral. So Q for the top part is the integral of dq. How do we find dq? How do we find how much charge is on each of these little slices? Well, a charge would be the density times the volume of that slice. So So the density of the charge is given by the charge distribution equation, the charge density that we were given initially in the problem. There's our density. If we take the density, multiply it by the volume of that little slice, then we'll get the total amount of charge dq. Since it's a volume of a little slice, we'll call that dV. How do we know what dV is? Well, a volume is area times thickness. Equals rho times the area A times the thickness dz primed. And we're going to integrate it. Okay, so here's an expression for the charge. We've got most of the hard work done now. Let's fill in our rho. Let's fill in our limits. Then we'll get the total charge on the top part here. If you're wondering why did I pick the top part, we'll see that in the next step when I fill in my density rho. So now for my next part, the total charge on the top part is the integral of our density rho. So now here we see that rho is some constant rho naught multiplied by 1, subtract absolute value of z. That's why I only took the top part. I don't want to fuss about the absolute value signs and worry if z is positive or negative. If we're only on the top, then z is positive. Z over A. So right here, drop absolute values because we're on the top. Where z is positive. Okay, so that deals with the density. Now we'll put in our thickness, A times dz primed. And our z means our z coordinate of our little slice, so that's z primed. Okay, so now where we can go from here, the last part we'll need is what is the limits of the integral. Here you have to be really careful in what we're doing. We're trying to find the net charge on the top part of that slab of what's within the Gaussian surface. So this part right here, inside my Gaussian surface, there's no charge on this right here. The only thing that's charged is what's shaded in pink. The only thing that's charged is the slab of charge itself. So my integral is going to start at the bottom of the top half. My integral will start at the bottom and will go to the top of the charged object. The top of the charged object has a coordinate of z primed equals A. So we integrate from the bottom to the top of the slab. Okay, so now this is an integral we can deal with without too much difficulty. Let's see what we're going to put in here. So we have the integral from 0 to A, and I can break this into two. We've got rho naught times A times dz primed, subtract the integral from 0 to A, rho naught times z primed over little a, the thickness of the slab, times A, the area of the Gaussian surface, dz primed. So there's our integral we're going to manage. Let's see what we get for that guy. So rho naught outside times A, outside the integral from 0 to A dz primed. Take our constants out front here too. Rho naught times area divided by thickness. Integral from 0 to the thickness of z prime times dz primed. The answers to these integrals are the integral of dz primed gives us z primed, going to be evaluated at a and 0. So that gives us a minus 0, which is just equal to a. The integral of z dz, this part, is equal to z prime squared over 2. That's evaluated at a and 0. Gives us a squared over 2. Subtract 0 squared over 2. That's just 0. Gives us a squared over 2. Okay, let's put these results in right here to get an expression for our charge. Equals rho naught times a times little a. So our constant in our density times the area of the Gaussian surface times the thickness of the slab. Subtract our constant times our area divided by the thickness times the thickness squared over 2. And we can simplify a tiny bit. So there's an expression which tells us the net charge inside the Gaussian surface. Okay, now the next thing we'll do is we'll put this net charge together with our net flux and we'll find the expression for the electric field.